Hello everyone, this is Abhinav Pandey and I am going to teach you text compression using Huffman coding. This particular coding technique was developed by David Huffman, a PhD student at Massachusetts in 1952 under his research paper, A Method for Construction of Minimum Redundancy Code. This particular coding technique is type of optimal prefix coding which is used for lossless data compression, and principal concept behind this is number of frequencies appeared in the text. The letter or character appearing multiple times will took less bits in the transmission, and the character or letter appearing lesser times will took more and more bits in the transmission. Kind of alliteration, you can say kind of alliteration, like India in Indonesia, Mississippi, Missouri, tonight lit a bright light. Like we can say in first text I and D appeared multiple times. In second text M, I, S, I, P appearing multiple times. And in the third text tonight lit a bright light, T, N, I, G, H, L, they almost every character appearing multiple times. There are several other examples, but we took tonight lit a bright light for our reference. Now let us see how many total characters are there in this text. So starting from TONIGHT, we have 22 letters and 4 spaces between tonight and lit, lit and A and bright and light. We have 4 spaces or dashes. Overall we have 26 characters in the text. In our standard ASCII representation, one character uses 7 bits and one parity bit. Overall 8 bit for transmission. So to transmit 26 characters, we need to send 26 cross 8, that means 208 bits. This is huge amount of bits. Now we'll start our coding technique. We'll see particular character or letter appeared how many times in entire text. So starting from T appeared 5 times in the text, tonight lit a bright light. O appeared once, N appeared once, I appeared 4 times, G and H appeared thrice, L appeared twice, A, B and R appeared once, and space appeared 4 times. Now we'll start arranging these characters in order of their appearances. T appeared most of time, so we'll put T in the leftmost side, and after T we'll put dash, I, G, H, L, O, N, A, B and R. We'll put R in the rightmost side. Now we'll start grouping different characters by bottom or right side. Like B appeared once and R appeared once. This will form a parental tree known as BR2. Similarly, N appeared once, A appeared once. They will form a vertical parental tree called NA2. Now we'll create trees for others: L2O1, G3H3, I4-4, T5-4. So we'll have a tree like this. Starting from B1R1, we'll form a upward going parental tree by calculating total number of bits and assigning them by going upward. So we are getting like GH6LO3, and this will get GHLO9, and similarly we are getting 13. -4 I4 creates -I8, T5 and -I8 creates T-I13, and overall we are getting 26 on the topmost side. So we can put a cross check here. We earlier calculated there are 26 characters required in the text, and here we are getting 26 characters too. So we are getting a cross check here. Now we'll assign branches. A left branch will be assigned as a 0 and right branch will be assigned as a 1. Starting from topmost, we are getting 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0 and 1. Now we will assign each and every character by a binary code via a path from up to down. Like we will start from top and get a code for each and every character. Starting from top, we are getting 0, 0 for T. Again we are getting a 0 in our path. We are getting another 0 in our path. So we got 0, 0 as T. Now we can write T as 0, 0 instead of a 8 bit in our standard ASCII representation. Now we'll assign for dash and I. we'll follow a yellow path for dash. Starting from top, we have a 0, then 1 and another 0. So we have 0 1 0 for dash. Now for I, we'll follow a blue path from top side. We have a 0, we have 1, and getting towards down we have another 1. So I can be represented as 0 1 1. Similarly, we can have codes for G, H, L, O, N, A, B and R, and writing these codes here they are. We are assigning codes for each and every character. Like G, for G we can write 1 0 0 0. For L we can write 1 0 1 0. Now have a look at N, how code for N can be written. Starting from top, we have 1 1 0 0. So we have 1 1 0 0, a 4-bit code for N. Now for R, 1 1 1 1. We have a 4-bit code for R, 1 1 1 1. Now we will calculate the number of bits required for the transmission of message after Huffman coding, and we will calculate the compression ratio. This compression ratio will help us to find out how many characters, how many bits we have saved after Huffman coding. So here we go. 2 bits are represented for T, so text has been reduced extensively. Now we'll find out how many characters appeared in entire text. T appeared 5 times in Tonight Lit a Bright Light, and here T can be represented as 0 0. So 10 bits required for transmission of T. Similarly, dash appeared 4 times, and dash is of 3 bits now, so it will take 12 bits. Similarly, other characters O, N, A, B, R, they appeared once and they are of 4 bits, so they will take 20 bits for transmission. Now we'll calculate how many overall bits we have to take for transmission after Huffman coding. Here it goes: 10 plus 12 plus 12 plus 12 plus 12 plus 8 plus 20. Overall 86 bits required. Earlier we saw that in standard ASCII representation, same message was transmitted with the help of 208 bits, and here we have only 86 bits. So you can say that Huffman coding saved a lot of bits in representation. Now we'll calculate compression ratio. Compression ratio can be calculated as bits before coding, bits after coding, and bits before coding. So we got 41.3%. Hence almost 60% data has been saved. So here Huffman coding gives us 60% of compression, 60% of saving. Like you can compare it like earlier for a commodity you are spending 208 rupees, and now for that particular commodity you are spending only 86 rupees. That is the difference. In textbooks usually probabilities of symbols are given, like T appeared 5 times in entire text, so probability is 5 by 26, 0.19. And in textbooks they used to write in from left to right instead of going from bottom to top. So their probabilities will be arranged, and a tree is formed from left to right side. There is not much difference in textbook representation and in my representation, but I found it more and more convenient going from bottom to top side. It enables us like forming a tree. It is more convenient. In my next video I will teach about Shannon